we are looking at weakest precondition, and we have covered all the primitive programming statements from the IMP programming language. So now we want to look at the compound programming statement. So first we look at sequential composition, right? So how to calculate the weakest precondition of f for the program C1 semicolon C2, right? So just to revise, right? So weakest precondition, right, as the name implies, is a precondition, right, which means it's a formula, right? It's a set of states from which you begin your execution of the program, which in this case is C1 semicolon C2, such that after the entire program finishes its execution, the state is guaranteed to be within this state f, right, within the set of states f, right, which is where f is a formula, right? So you are encoding a set of states using a formula, and you want to find out another formula, right, which encodes the weakest precondition, right, which is essentially encoding all those states such that executing C1 semicolon C2 will lead you to a state in f, right? Is guaranteed to lead you to a state in f. Okay. So again, we want to express this weakest precondition using the weakest precondition for the individual statements, right? So I want to use the weakest precondition for C1 and the weakest precondition for C2, right? So since this is backward propagation, right? So we want to propagate this set of states f backwards through the program. So you will first calculate weakest precondition, right, of let us say f, right, with C2, right. So this will give you all the set of states such that on executing C2, you are guaranteed to be in a state in f, right? So a set of states such that on executing just C2, you are guaranteed to be in the set f, right. And now we can take this as input for the weakest precondition for C1, right. So weakest precondition of this particular formula with C1. Okay. So this is essentially saying that give me all the set of states such that on executing C1, I am guaranteed to be in a state in WP f comma C2, and I know that on guaranteeing C2, or rather I know that on executing C2 on such a state, I am guaranteed to be in a state in f, right. So therefore that guarantees that after executing C1 followed by C2, you will be in a state in f, right. So it's given by WP of f comma C2 comma C1. Okay. Now as an exercise, right, we will try to prove this formally, right. So this is an exercise which we haven't done earlier for strongest post condition, right, but for weakest precondition, let us try to prove this statement formally, right. So formally meaning that we want to show that these two sets are equal, right. So we will show that instead of taking a formula f, right, we will just use a set of states s. So we know that a formula f just encodes a set of states, so let's just take a set of states, right. So we will formally prove that WP of S C1 semicolon C2 is equal to this right hand side, right, which is WP of S comma C2 comma C1, right. So the advantage of taking a set of states, right, is that this WP, right, itself is now a set, right. So both these are sets. So we essentially want to prove that two sets are equal, and the way to prove that two sets are equal is to show that the left hand side is a subset of the right hand side, and vice versa, right, that the right hand side is a subset of the left hand side. Okay. So let's prove both the cases, right. So we'll prove first, let us prove first that the right hand side is a subset of the left hand side. Okay. So both these are set of states, right, they are set of valuations. So we want to take a valuation in the right hand side and show that it is also present in the left hand side, right. So consider a sigma which is, let's say, in the right hand side. Okay. And we will show that this sigma is also in the left hand side. Okay. And we will prove this just for using the definition and the operational semantics of sequential composition. Okay. So let's consider a state sigma which is in the right hand side. So that means that sigma is in this particular set, right, WP S comma C2 comma C1. Okay. Now let's just use the definition of weakest precondition, right. So the definition of weakest precondition says that if sigma is in this particular weakest precondition, then on every execution of C1 on sigma, you are guaranteed to be in a state here, right. So that's just the definition, right. So for all, let us say, sigma prime if sigma C1 goes to sigma prime comma skip. Right? So when you finish the execution of C1, then it is guaranteed that such a sigma prime is going to be in WP S comma C2. Right? So we are just applying the definition of weakest precondition, the outward weakest precondition, right, which is this one. So for the outer weakest precondition, this is essentially like the target set of states, right. So we are just saying that on executing C1 for all executions, right, of C1 on sigma, if the execution of C1 finishes, then you are guaranteed to be in this target set of states, right, which in this case is WP S comma C2. Okay. And okay, so this is just coming from the definition of weakest precondition. Okay. Now let us see what we have to show, right. So we need to show that this sigma, so let me just call this as 1, right, as result 1. So we are going to use this result 1 later, but let's now focus on what it is that we want to prove, right. So we want to prove that this sigma is in the left hand side. So to prove that sigma is in the left hand side, I need to show that on executing C1 semicolon C2, right, finishing the execution of C1 semicolon C2 on sigma, I am guaranteed to be in a state in S. So this is what I have to prove, right. So let us say that, suppose let us consider some sigma double prime such that if I execute C1 semicolon C2 on sigma, and suppose I reach the state sigma prime. Okay. So in order to show that sigma is in this weakest precondition, right, of S C1 semicolon C2, I will have to show that this sigma double prime is present in S, right. So if I take any execution of C1 semicolon C2 on the state sigma, right, and if such an execution leads me to the state sigma double prime, then this sigma double prime is guaranteed to be in S. If I can show that sigma double prime is in S, then that will mean that the sigma is also in the left hand side, right. So it's in WP of S C1 semicolon C2. So again, this is coming from the definition, right. So in order to show, right, that the sigma is present in the right hand side, in order to show that sigma is present in the right hand side, I need to show that for all sigma double prime, right, if sigma C1 semicolon C2 goes to sigma double prime comma skip, then that should imply that sigma double prime is present in S, right. So we need to prove this particular implication, right. So I am proving this implication by assuming the antecedent, right. So I am considering a sigma double prime such that on executing C1 semicolon C2 on sigma, I go to sigma double prime, and I will show the consequent, right, which is that I will show that sigma double prime is also present in S. So if I can do that, then I am done. So that would mean that sigma is present in WP of S C1 semicolon C2. Okay. So now we need to show that this sigma double prime is present in S. Okay. But let's see what information we have, right. So what can we deduce from this particular statement, right, that executing C1 semicolon C2 on sigma leads me to the state sigma double prime, right. So from the operational semantics, I know that to execute C1 semicolon C2, you would first need to execute the entirety of C1, right, which means C1 should have been converted into skip, and then from that state, right, you would then execute C2, right. So therefore there must exist some sigma prime, right, such that on executing C1, I must have gone to that sigma prime, right, and on executing C2 on that sigma prime, I must have reached sigma double prime. So this is the only way that the execution of C1 semicolon C2 on the state sigma can lead to sigma double prime, right, which is that first you must have executed the entirety of C1, which would lead to the state sigma prime, and then on that sigma prime you would execute the entirety of C2, right, which will lead you to the state sigma double prime. Okay. Okay. So now I know that such a sigma prime exists, but now I can use my equation number 1, right. So the equation number 1 says that if sigma C1 goes to sigma prime comma skip, then that sigma prime must belong to WP S comma C2, right. So from 1 I can gather that sigma prime must belong to WP S comma C2. Okay. And now what is the definition of WP S comma C2, right? So since sigma prime is in WP S comma C2, I know that for all sigma double prime, right, if on executing C2 I go to sigma double prime comma skip, then this should imply that sigma double prime must be in S, right? So this is the definition again. So because sigma prime is in WP S comma C2, right, it is the weakest precondition of S with respect to C2, I know that on executing C2 on sigma prime, on any execution of C2 on sigma prime, it must lead me to a state which is in S, right? So in this case I know here, right, that on executing C2 on sigma prime, I reach the state sigma double prime, but from the definition I know that sigma double prime must be present in S, right? So therefore again by definition of weakest precondition, the sigma double prime must be present in S, and this is exactly what we wanted to prove, right? So because sigma double prime is in S, right, therefore this sigma, right, since I know that the sigma double prime is obtained by executing C1 semicolon C2 on sigma, and any such sigma double prime is in S, right, therefore sigma must be present in WP of S C1 semicolon C2, right, which means that sigma is present in the left hand side. Okay. So this shows that the right hand side is a subset of the left hand side. Okay. So I started with a sigma which is in the right hand side, and I deduced that such a sigma must also be in the left hand side, right? Therefore the right hand side is a subset of the left hand side. Okay. So this is the proof of the right hand side subset of the left hand side, right, which we have just seen. Okay. Okay. So now let us prove the other direction, right, which is that the left hand side is a subset of the right hand side. Okay. So here I am going to start with, let us say, some state sigma, okay, which is in the left hand side. Okay. So which means that sigma is in WP of S and C1 semicolon C2. Okay. And I need to show that such a sigma is also in the right hand side. Okay, so as usual, right, let us first expand the definition of WP. So I know that, so since sigma is in WP of S C1 semicolon C2, this means that for all sigma double prime, right, or let us call it sigma prime, if on executing C1 semicolon C2 on sigma, right, I reach sigma prime, then this sigma prime must belong to S, right. So this is just from the definition of weakest precondition. Okay. Since sigma is in WP S C1 semicolon C2, that means that on executing C1 semicolon C2 in sigma, if it leads me to a state sigma prime, it must be in S. Okay. Now again, right, let us kind of expand on this particular definition, right. So we know that if on executing C1 semicolon C2 you can reach sigma prime, then you would have first executed C1 on sigma, and then you would have executed C2 on sigma, right. So that's the only way that that you can reach that you can finish the execution of C1 semicolon C2. Okay. So let us consider this scenario. Let us consider the execution of C1 first, right. So suppose on executing C1, I reach some state, let us call it sigma double prime. Okay. So suppose on executing C1, I reach the state sigma double prime. Now what is it that I can say, right? So since I am reaching the state sigma double prime by executing C1, on further executing, or rather on further execution of C2 on this sigma double prime, I must be in a state which is in S, right. So for all sigma double prime such that, rather let me call this sigma prime. So for all sigma prime such that on executing C2 on sigma double prime, if I reach sigma prime, then the state sigma prime must be in S. So how do we know this? Because I know that this sigma double prime is obtained on executing C1 on sigma. Now if I take any such state, right, if I execute C2 on sigma double prime and I reach the state sigma prime, that essentially means that I have executed C1 semicolon C2 on sigma, right, because on executing, so from sigma, right, on executing C1 I reach the state sigma double prime. Now if I take any execution, right, of C2, there could be multiple executions of C2, right, which may lead to multiple different states, but whatever state it leads to, right, which in this case is this sigma prime, the sigma prime is effectively obtained by executing C1 followed by C2 on sigma. And I know, right, from this, let's call this as equation 1, right. So from equation 1 I know that on any execution of C1 semicolon C2 on sigma, if I reach the state sigma prime, that sigma prime must be in S, right. So therefore from 1, right, we can show that for all sigma prime, if sigma double prime comma C2 goes to sigma prime comma skip, then this sigma prime must be in S. Okay. So what is this, right? So if you carefully notice this, right, this is just saying something about the state sigma double prime, right. So it's saying that if you execute any execution of C2 on sigma double prime will lead you to a state in S, right. So this means that sigma double prime must be in WP of S comma C2, because on executing C2 on sigma double prime, I am guaranteed to be in a state which is in S, right. So I will never go outside S. This is exactly the definition of WP S comma C2, right. So WP S comma C2 would mean that on executing C2 on sigma double prime, you must be guaranteed, right, on every execution you must be guaranteed to be a state in S, which is indeed the case, right. So that's exactly what we have shown. Okay. So since sigma double prime is in WP S comma C2, okay. Now where did this sigma double prime come from, right? So we said that suppose sigma C1 goes to sigma double prime comma skip, right. So we took any arbitrary sigma double prime that is obtained by executing C1 on sigma, and we have shown that such a sigma double prime must be in this set, right. So again, by definition of weakest precondition, this would mean that such a sigma will be in WP of S C2 comma C1, right. Why is that? Because what we have shown is that if you execute C1 on sigma, right, any execution of C1 on sigma which leads to a state sigma double prime, we have shown that such a sigma double prime must be in this set, right. So this is directly coming here, right, which is in WP S comma C2, right. So any execution of C1 on sigma is guaranteed to lead me to a state which is in WP S comma C2, and therefore sigma itself must be in WP of S comma C2 comma C1, and this is exactly the left hand side, right. So sorry, right hand side. So we have shown that sigma belongs to the right hand side. Okay. So this completes the proof that the left hand side is also a subset of the right hand side, right. And notice that in this proof, right, all we have used, so we used two things, right. We have used the definition of weakest precondition, right, and we have used the operational semantics for sequential composition, right, which is to break down the execution, right, of C1 semicolon C2 into the execution of C1 followed by the execution of C2. Okay. So that's the proof. So this finishes the proof, right, of our required statement. Okay. So let's look at if then else now. So now we want to calculate the weakest precondition for F if G then C1 else C2, right. So intuitively, right, this means that we want to find out the set of all states such that on executing this if then else, right, you are guaranteed to be in a state in F, right. So what are all the states from which if you execute this if then else, then you are guaranteed to be a state in F, right. So again, we want to express this using the WP of C1 and the WP of C2, right. So if you take a state, right, let's take any start state. right? Either it satisfies G or it doesn't satisfy G. Okay. So either you will execute the if conditional or the if branch, or you will execute the else branch. So if a state satisfies G, then obviously then the execution will proceed along the if branch. Now you will execute C1. So you want to guarantee that on executing C1 you will always end up in a state in F. That is simply weakest precondition of F comma C1. So weakest precondition of F comma C1 are the set of all states such that if you execute C1 on such a state, you are guaranteed to be in a state in F. But we will execute C1 only if the state satisfies G, right? The start state satisfies G. So therefore we have an implication. So if the start state satisfies G, then it should also satisfy WP of F comma C1, which in turn will guarantee that on executing C1, you are always sure to be in a state in F, right? A state which satisfies F. So this is for the if branch. For the else branch, so again we want to guarantee that if the else branch is executed, which is C2, you are guaranteed to be in a state in F, but the else branch will only be executed if the start state doesn't satisfy G, right? So this is not of G should imply that WP of F comma C2, right? And then we have the conjunction, right? So either the start state satisfies G or it doesn't satisfy G. If it satisfies G, it should also be in WP F comma C1. If it doesn't satisfy G, it should be in WP F comma C2. So this is the formulation. Okay. Now again let's try to prove this formally. Right? Okay. So again, right, let's do this exercise. So here we have two formulas, right? So we want to show that these two formulas are equivalent to each other. So we will show that LHS, right, implies RHS and RHS implies LHS. Right? So if you show that both these implications hold, that would mean that LHS and RHS are equivalent to each other, right? And we will again use the definition of weakest precondition. Okay. So let's first prove that LHS implies RHS. So to prove that LHS implies RHS, let us take a state sigma which is a model of LHS, and we will show that such a sigma must also be a model of RHS, okay, which in turn will show that LHS implies RHS. Okay. So suppose sigma is a model of LHS. So use the definition of weakest precondition. So that means that for all sigma prime, right, if on executing this if then else, right, so if G then C1 else C2, if you reach the state sigma prime comma skip, then you are guaranteed that such a sigma prime must be a model of F, right. So here we are encoding a set of states using formula, so that's why we are using the models of operator, right. So any execution of the if then else on the sigma, right, which is a model of the LHS, would lead you to a state sigma prime which should be a model of F, right, which is the target set of states. So this is by the definition of weakest precondition, right. So by definition of weakest precondition, this is what we get. Okay. So now let's call this again as equation number 1. Okay. So we are going to use this later. Let's focus on the RHS for now, right. So I want to show that sigma is a model of RHS, right. So that's a conjunction, right. So I need to show that sigma is a model of both the left conjunct and the right conjunct. Okay. So suppose sigma is a model of G, right. So since each of these conjuncts are implications, right, so I need to show that if sigma satisfies the antecedent, it will also satisfy the consequent, right. So in this case, suppose sigma is a model of G, then I also need to show that sigma is a model of WP F comma C. So if sigma is a model of G, then I know by the operational semantics, right. So by the operational semantics, I know that if I execute this if then else on sigma, since sigma is a model of G, it must lead you to the state sigma comma C1. Right? So this is one of the rules for if then else, right, that we had one of the transitions for if then else that we had studied back when we went through the operational semantics of the imp language, right. So, which is that whenever you want to execute an if then else statement, right, on some program state, you will ask, okay, does the program state satisfy the conditional? So, if it satisfies the conditional, then you can simplify the program to just the if branch. Okay. So, by the semantics, I know that this must be true. Okay. Okay. So, now I need to show that the sigma is a model of this particular thing, right, which is WP f comma C1, right. So, again, right, suppose on executing C1 on sigma, I reach some state, let us call it sigma prime. Okay. So, consider some arbitrary sigma prime such that on executing C1 on sigma, I reach that state sigma prime. So, to show that sigma is in WP f comma C1, I would need to show that this sigma prime is in S, rather sigma prime is in F, right. So, if I can show that sigma prime is a model of F, that would mean that sigma must be in WP f comma C1, right, because sigma prime is any state obtained after executing C1 on sigma. Okay. So, again, from the definition of weakest precondition, if I can show that sigma prime is in F, then I am done. Okay. Now, what can you say about these two things, right? So, on executing the if then else statement on sigma, I reach sigma comma C1, and on executing C1 on sigma, I reach sigma prime. So, I can combine these two, right. So, from these two statements, right, it is clear that on executing the if then else statement on sigma, I am actually reaching the state sigma prime, right, because since sigma is a model of G, I am actually first going to the if branch, and then I am executing the if branch to get sigma prime. Okay. And now our equation number 1 is going to help us, right. So, equation number 1 says that on executing the if then else on sigma, if you reach a state sigma prime, then that sigma prime must be a model of F, right. So, from 1 I can directly deduce that sigma prime must be a model of F, and this is exactly what we wanted, right. So, then by definition of weakest precondition, sigma, right, must be a model of WP f comma C1. Okay. So, we started with sigma is a model of G, and we showed that sigma is also a model of WP f comma C1. Right. Similarly, right, if you start with sigma is a model of not of G, then you will be able to show that sigma is a model of WP f comma C2, right. So, again, if you start with sigma is a model of not of G, which means sigma is not a model of G, then by the operational semantics, right, here you would actually reduce to C2, right, because sigma is not a model of G, and then you can again use equation number 1, right, to show that executing C2 on such a sigma is always guaranteed to lead you to a state in F, right. So, therefore, such a sigma would be a model of WP f comma C2, right. So, using these, right, we have essentially shown that sigma is also a model of the right hand side. Okay. So, we started with sigma as a model of the left hand side, and we showed that the sigma is also a model of the right hand side, okay, which shows that left hand side implies the right hand side. So, I have skipped that particular step, right, where you start with sigma is a model of not of G, right, and then you show that sigma is a model of WP f comma C2. Okay. As homework, right, you can also try to show this right hand side implies the left hand side, right. So, for this you would need to take a sigma which is a model of the right hand side, right, and then show that such a sigma would also be a model of the left hand side. So, as homework you can try to prove the other direction. Okay. Okay. Let us look at some examples now. So, now that we have computed this generic formulation, right, whenever you have an actual example, all you need to do is you need to just plug in, right, the formulas from the example into the definition. So, here I want to find the weakest precondition for y equal to 0. So, this is F for this particular if then else, right. So, I just plug in the definition. So, this is G, right. So I get x is greater than 10 implies weakest precondition of f, which is y is equal to 0, and C1, right, which is y colon equal to z plus 1. This is the first conjunct, and the second conjunct, right, which is not of g. So x is less than or equal to 10 implies weakest precondition of y is equal to 0 and y colon equal to z minus 1. Okay. So this is what you get by just applying the definition. Now I can further simplify this, right. So what is weakest precondition of y equal to 0 and y colon equal to z plus 1? So this is something that we had covered earlier, right. So the weakest precondition for the assignment statement, right. So if you have formula f and if you have an assignment statement x colon equal to e, then this weakest precondition is simply given by f where e replaces x, right. So it's just simple syntactic substitution, right. So here I have the formula y equal to 0 and then y colon equal to z plus 1. So which means that wherever I see y in this formula, y equal to 0, I am going to substitute it by z. I am going to substitute it by z plus 1. Right? So this will give you x is greater than 10 implies z plus 1 equal to 0, right, which is same as z equal to minus 1. And similarly the other day, right. So x is less than or equal to 10 implies, again, right, wherever I see y, I substitute it by z minus 1, so I get z is equal to 1. So again, intuitively, right, if you execute the program beginning on this state, right, then if you execute the if branch, you will get y is equal to 0, right, because z is minus 1 and you are doing y equal to z plus 1, right. So it will guarantee that y is equal to 0. If you execute the else branch, then you again it is guaranteed that y will be equal to 0.